So this will be the logic part of combinatorial logic afternoon. And it's wonderful to have Artem Chernikov speaking about hypergraph regularity and higher arity VC dimension.
Hi, everyone, and thank you very much for giving me an opportunity to present here. To be honest, there's not going to be too much logic in my talk per se. So there is logic in some of the proofs that I most likely won't be presenting today. And also there are some motivations and connections to logic. But actually, for the talk, there will be very little logic visible in it in any explicit form. So the title of the talk is Hypergraph Regularity and Higher Arity VC Dimension. Let me begin. Oh, and it's a joint work with Henry Tausner, who I think is also present in case there are maybe some questions in the chat, etc. So I would like to begin by fixing some very basic notation just to make sure we're on the same terminological page. So in this talk, whenever I say graph, which I will usually denote as G, with two sets of vertices V1, V2, and the relation E, I will mean a bipartite graph. So E is a subset of V1, the direct product of V1 and V2. Okay, no requirements of symmetry or anything imposed, just a binary relation like this. I will also talk about induced subgraphs. So an induced subgraph of G is a graph H with parts, let's say we denote them W1, W2. And the edge relation is the one induced from the original graph. So the edge relation is just E restricted to W1 times W2 for some subsets Wi subset of Vi for I equals 1 or 2. Okay, so we have graphs of this form V1, V2. Some edges, and an induced subgraph is when we fix some subset of each side of the partition, and we look at all edges induced from the relation of the original graph, restricting to this product of these two subsets. Okay. So we will. The rest of the discussion will be in this partite setting. It doesn't make much difference to talk about usual graphs. I mean, they can be considered by just taking V1 equals to V2 and assuming that the relation is symmetric and without loops. Yeah. So it's, but I'll stick to this partite setting for simplicity of notation. All right. So now, what is the intuition or motivation for some of the theorems that I would like to present today? So intuitively, one can say that for a fixed finite graph H, every sufficiently random G contains H as an induced subgraph. Of course, to make this precise, we have to define what random means, etc., right? But intuitively, if let's say we pick edges with some fixed probability, then assuming the graph is large enough, G is large enough, it is going to contain H as an induced subgraph. Okay, and the expectation is that if some induced subgraph H is forbidden, should imply that some structural results can be proved about G. So some structure on G. So to give you a trivial example, we can consider the situation when, for example, H is just one edge between two vertices. Okay. So then if G is H-free, of course, we get that G is the empty graph, yeah, the graph without any edges. So then G is just a graph of the form V1, V2, and no edges whatsoever. If it doesn't contain H as an induced subgraph. Similarly, if we take H, let's say, to be the non-edge, yeah, then GH3 implies that G is complete. So it contains all the possible edges. So the edge relation is V1 times V2. And what we would like to understand is what happens when H is arbitrary. Okay, so is there some structural decomposition of G which can be established assuming that G omits a fixed induced subgraph H, but without knowing anything in advance about H? So of course, note that H in this case is bipartite, right? As all the graphs I'm considering for now. Okay, so let me start by stating a result which has appeared in several variants. So the earliest variant is probably, I believe, is due to Alon-Fischer-Newman from 2007, and a different variant in the more general measure setting is due to Lovász-Szegedy from 2010. So the theorem is as follows. So assume H is any finite graph so again, in the sense that I defined on the previous slide, yeah, so it's a bipartite graph, any finite graph, and assume that epsilon is an arbitrary positive real number. Then there exists some natural number n depending just on these two parameters, so the finite graph H and positive real number epsilon, which satisfies the following. So whenever we are given a finite graph G with parts V1, V2, and the edge relation E, any finite graph, which is H3, okay, then there exist sets A1 through A capital N, subsets of V1, and sets B1 through Bn, subsets of V2, such that if we consider the relation E prime, which we take to be the union of the products of the corresponding sets in these two sequences, so the union of the products of boxes AI times BI for all I between 1 and n, then we have that the symmetric difference between the original relation E and this relation E prime, given by the union of boxes is very small. So small in the sense that the error is smaller than epsilon times the total possible number of edges. Yeah, so V1 times V2. So this is the theorem. So for any fixed H and error epsilon, all H3 graphs up to the small error, up to symmetric difference epsilon, are actually given by unions of boxes. Yeah. So if we draw a picture, let's say this is V1, this is V2, and this is the incidence matrix. So it means that we can pick some boxes where the number of boxes is always bounded by n. Not the boxes, sorry, the number of the sides of boxes is bounded by n. Such that the graph is approximately given by the union of boxes. So some points maybe are missing, some additional points are present, but approximately it's the union of these boxes. Okay. Moreover, some more information is known in this case. So first of all, the number of the sets that we need to pick can be bounded by a polynomial in terms of 1 over epsilon. So in terms of the inverse of the error, for some d, so the power which depends only on this finite graph H. Okay, and later in the talk we will see this bound more explicitly. Also, each of the sets, so each AI BI, is in fact in the Boolean algebra generated by the fibers of the graph E. Generated by the fibers of E. So what do I mean by fiber of E? So for example, if I fix a point in one of side of the part in one of the parts, so for example for A and V1, we can consider the fiber EA, fiber or neighborhood, depending on which terminology you prefer. So this is just the collection of all, let's say, B in V2, such that AB is in E. Oops. And similarly for fibers on the other side of the partition. Yeah. So similarly, we consider subsets of V1, which are given by all elements in V1, which are connected to a fixed point in V2. Okay. So we have these two additional conditions that one can ensure. Maybe let me also remark that there are some variants of this theorem that were discovered in model theory, in particular in some work of Khrushchevsky and co-authors, and in communication complexity, and in some other topics. So it means a rather well-known result throughout several combinatorics adjacent areas. Okay, so this is the theorem. Now, my point today is to present a generalization of this result to hypergraphs. And also later on, I will comment how this can be viewed as a strong form of regularity lemma for graphs or for hypergraphs in the generalized theorem. Okay, but this is the result, the motivating result for graphs. So now I would like to state a variant of this for hypergraphs. So the new theorem. If there are any questions, please ask them. Okay, so for hypergraphs now, the notation is very similar. We're again going to be working in a partite setting. So we say that the k hypergraph, which I will still keep denoting by G, is given by k sets, V1 through Vk, and E, a net relation, such that E is a subset of the product of these sets. So I from 1 to k. Okay. This is the meaning of hypergraph for me. Similarly, we define, in a completely analogous manner, we can define induced k hypergraphs. Okay, so this are sets of the form H, k hypergraphs of the form H with some V1, let's say W1 through Wk, and E restricted to the product of the W's for some choice of subsets Wi of Vi. Okay. And I also want to define what it means to contain a hypergraph of smaller arity as an induced hypergraph. So let's say I have some k less than k prime, and I have H a k hypergraph, and G a k prime hypergraph. Okay. Then we will say that G omits H if for any fixed k prime minus k coordinates. So for example, we fix the first k, for example, we fix the last coordinates. So we have a k plus 1 through a k prime in the corresponding product vk plus 1 times etc. times vk prime. Yeah. So if we fix all but k coordinates, we can consider the corresponding hypergraph, k hypergraph induced on the remaining coordinates. So then H is an induced hypergraph of the corresponding set of vertices. So tuples x1 through xk, such that the whole tuple x1 through xk with the remaining coordinates substituted by ak plus 1, etc. through ak prime belongs to E. Okay, oh, sorry. So I'm defining what it means for G to omit H, right? So then I should say then the hypergraph given by this omits H. Sorry, yeah. So any hypergraph given by fixing all but k coordinates omits H. Okay, hopefully this is clear now. All right, and so the last thing I want to define for the hypergraph terminology are the so-called cylindrical cells. So if I'm given two natural numbers, r less than k, we consider a certain Boolean algebra, BKR, sorry, is the Boolean algebra of subsets of the product set, so the product Vi, over all I from 1 to k, generated by intersections of k-ary cylinder sets So what do I mean by this? i.e. sets of the form as follows. So sets of the form X. So we consider all tuples xi of length k belonging to the product of the VIs. So I from 1 to k, where the set is determined by fixing a bunch of conditions, but each of these conditions is only allowed to talk about k coordinates at a time. So we have that for all sets, S subset of the set k, which is the standard notation for the set of the natural numbers 1 through k, such that the size is less or equal than R, and such that the corresponding subtuple. So we have this tuple of length k, and now I'm considering the subtuple of length at most R, which corresponds to those indices which are in the set S. Okay, so this belongs to the set XS for some choice of the sets XS, subset of the product of the VI, but now I is an S. Okay, let me see, there's some question. Is the definition circular? Let's see, maybe what I wrote is not correct. So G omits H if for any fixed choice of all but k coordinates, the resulting k hypergraph omits H. Yeah, so I'm not sure, it seems okay to me. So we have the product here over all I from 1 to k, Vi. Right, oh yeah, sorry, I see, that's the point, yeah. So we already defined when k is equal to k prime, yeah? This is just the natural meaning of omit. But now I want to also be able to talk in some sense about omitting hypergraphs of smaller arity within graphs of higher arity. And so we define it in terms of the previous definition by saying that whenever I fix some k-ary fiber of my hypergraph E, then it omits H. Okay. All right. Now, okay, yeah. So now we have this such sets, intersections of cylinder sets. So intuitively, you can think about it as just saying that the indicator function, so this equivalent to saying that the indicator function of the H relation is a product of functions depending only on on at most R variables. So is a product of functions depending on at most R variables. Okay. So we can impose all such conditions, but no condition can involve more than R variables at a time. Okay.
So previously you were talking about finite objects, but this only makes sense for infinite ones, I guess. If you take the full Boolean algebra.
Right, but I will talk about bounded sets of bounded complexity in this algebra.
No, I understand.
Later on. Yeah. But as of now, yeah. So this is only meaningful for infinite sets per se. Yeah.
Yeah. Fine.
Yeah. Thank you. Yes. Okay. So right. Yes. So this is the okay. So this is our definition. So now let's. I think I have everything to state the result. Oh well, maybe first let me give a quick example. So if we look at the case, let's say B21. So these are just products of sets as we considered earlier. Yeah. So B21 consists is the Boolean algebra generated by rectangles. So this is the algebra generated by sets of the form A times B for A subset V1, V1 B subset V2. Say. Okay, and so now we can state the theorem. Oops, I don't know why this keeps happening. Theorem, which is a hypergraph generalization of the result of Alon-Fischer-Newman and Lovász-Szegedy. So for any k less or equal than k prime, so we fix these two arities. Any finite k hypergraph H and any real number epsilon bigger than 0, the error term, there exists some natural number n depending just on these parameters. So n of h, k, k prime, epsilon, which satisfies the following. Okay, so if we have G, an arbitrary finite H-free K prime hypergraph. Okay, so it doesn't contain H as an induced K hypergraph. Then for some E prime, so another relation of arity K prime, so I from 1 to K prime, a union of at most n sets, at most n sets, okay, so I should say, as Udi remarked, I should say at most n intersections of cylindrical sets, of intersections of cylinder sets in B K prime K. We have the symmetric difference between the original hypergraph E and this relation given by union of cylinders is small. Yeah? So it's at most epsilon times the total measure of vertices of possible edges. So the product of the cardinalities of the parts Vi for I from 1 to K prime. Okay, so this is a theorem. So we can approximate, essentially it's saying that if we have a relation of arity k prime, and it omits an arbitrary finite hypergraph of arity k, then the whole relation can already be approximated with arbitrary precision and uniformly, because n only depends on the choice of this initial data, by sets of arity k, essentially. Yeah, so sets which only involve k variables whose definitions only involve k variables at a time. Okay, so this is of course in the case k prime equals 2, this gives the original result, so the previous fact, except for the specific bound. So the bound there was polynomial, if you remember, in terms of the error, in terms of 1 over epsilon. So here we are not stating it. In fact, any kind of optimal bounds here are very open. So currently our proof uses some infinitary techniques. Some compactness arguments are involved. We have some idea how to bound it maybe, but it hasn't been worked out yet. So for now, we just know that there is a uniform bound. Okay, maybe I can say something later about this. All right, let me make a couple of remarks concerning this theorem. So the first remark is that the case k prime and k, so k prime arbitrary and k equals 1, sorry, k equals 2 is due to myself and Starchenko, some earlier work. Now, also the theorem is proved in at a much larger level of generality. So this is essentially a measure theoretic result. So it works for arbitrary measures on vertices. So here I stated it for uniform measure on the vertices, yeah, in this counting bound, but it works with arbitrary choice of measures on the vertices. So for arbitrary measures on vertices, we can also consider, instead of graphs, we can actually consider real valued functions. So valued in some bounded interval, for example, 0 valued functions instead of graphs. And also, we have more information about the sets. So we don't have to consider actually arbitrary intersections of cylindrical sets. We only need to consider those which are given by the fibers of E. Okay, so the sets, so the cylinder sets in the result are given or can be chosen to be given by the fibers of the original hypergraph E. By fibers of various arities smaller than k. Yeah? So when we fix all but k coordinates and to look at the corresponding fiber of E, so in fact everything is built out of such already. Okay. Oops. Let me see, there's some question in chat. 0, 1 valued function. I see. So yeah, here one needs to be a bit careful, but basically the idea is that you view H as it means that you fix some gap. Let's say you fix some R1 less than R2 in the interval 0, 1. And then when the function takes value bigger, greater or equal than R2, you view it as the edge. And when the function takes value less or equal than R1, you view it as the non-edge. Yeah. So we think about that so we need to enforce that there's some separation. It can be as small as you want, but there's some separation and between the values which correspond to edges and non-edges in this picture. Okay. So this is the statement of the theorem. Now I would like to say some words how VC theory comes into the picture, and also what the higher arity VC theory means in the title. So connections to VC theory, to VC or Vapnik-Chervonenkis. Okay, so this, of course, rather important collection of facts in computational learning theory, I guess originally, or probabilistic learning, but which permits a lot of things in combinatorics and in model theory. In fact, it was independently discovered in model theory around the same time. Well, some elements of VC theory. So let me just define a couple of things that we will need. So first of all, let's define what VC dimension of a family of sets is. So assume a given F, a family of subsets of a given set V. Okay, so by P I denote the power set of V. So we have a collection of subsets of V. Then we say that this family has VC dimension equal to D, a natural number D. If D is the maximal number, such that there exists some set X, subset of V, of size D, such that all subsets of the set can be shattered by sets in the family F. So what does it mean? It means that for any Y, a subset of X, there exists some set S in our family F, such that if we look at X intersected with the set S, we get precisely Y. Okay, so we have the set V. Now the VC dimension is D. If it's possible to find some subset of size D, so this is X, right? Such that when we run through the sets in the family F, all subsets are given by intersecting these sets with the set X. So we get the full power set by looking at the intersections of sets in the family with X. Okay. And we say it's infinity if there is no such D, that the VC dimension of F is infinity if there is no such D. Okay. There are two fundamental facts, well, which are related. I mean, one is used in the proof of the other, but for us, for this talk, the two relevant facts are first, the Sauer-Shelach lemma, which bounds the number of sets that can be cut out from sets of given size by a family of given VC dimension. So assume we know that the VC dimension is D, or less or equal than D, I guess we can say. Then for all natural numbers n, if we take any set X, a subset of V of size n, and we look at the family of all subsets of the set X that can be obtained, that are cut out by sets in the family F. So all Y such that Y is given by X intersected with S for some S and F. Okay, and the number of such sets is bounded by n to the power d. Okay, so it's polynomial, first of all. Of course, in general, for a general family of sets F, it's going to be exponential. It's possible, it's 2 to the n. It's possible that we pick out all the subsets. But there is this dichotomy between polynomial and specifically polynomial of degree d, where d corresponds to the VC dimension of F, and exponential growth for such families. Okay, so this is the Sauer-Shelach lemma. And we also have a very important fact, the existence of epsilon nets of bounded size, I guess, existence of epsilon nets. Or a stronger variant of this result, the so-called VC theorem. So, okay, but we'll only need epsilon nets. So this is due to, I guess, originally due to Hausler-Welzel. There are probably various improvements on the bounds, but I'm not going to focus on that. So, okay, so what does it tell us? It tells us that if we have a family of sets in some probability space, we have a family of of sets of positive measurable sets in some probability space, then it's possible to pick a transversal for this family of size bounded in terms of the BC dimension and the positive measure that we want to consider. So to be precise, for every natural number d and for every epsilon positive real number, there exists some natural number n, depending just on these two parameters, such that, and let me just state it for finite probability spaces. So for any finite probability space, to avoid the discussion of measurability, it's more general. The result is more general, but there are some measurability assumptions needed in general. So for any finite probability space, let's say V and the measure mu, giving weights to the points in V, and any family of subsets of V, such that the VC dimension of this family is bounded by D. There exists an epsilon-net for this family, by which we mean that there exists some points x1 through xn in the set V. So n is bounded, yeah. So it's of bounded size, independent of the actual family or measure. So such that for any set S in the family F, if the measure of the set is at least epsilon, or greater than epsilon, then one of these points belongs to the set. So xi belongs to S for some I. Okay, so this is an important fact about families of finite VC dimension. In fact, a random sufficiently long sample is going to give an epsilon-net almost surely. Yes, so it's in fact stronger than just the existence. In fact, it's a very typical behavior for long enough samples. Okay, so now what does it have to do with the previous discussion, in particular with the result of Alon-Fischer-Newman and Lovász-Szegedy? Well, so we see that the connection is actually quite straightforward. So given a graph G, so as before, so two parts V1, V2, and the edge relation V, we can define the VC dimension of this graph to be the VC dimension of the family of its fibers. So let's say the VC dimension of the family EY, subset of V1, such that Y varies over all elements in V2. Okay, so this is a family of subsets of V1. So it makes sense to talk about its VC dimension. We pick a choice of the site. For the question of finiteness of VC dimension, it's not important because by duality for VC dimension. So if we only care, let's say, about finiteness or up to exponential drop, the choice of the site doesn't matter. So we can alternatively look at fibers on the other side. Okay, so now note that G emits H. Let's say H is given by W1, W2, and E restricted to W1 times W2, such that both parts have size at most D. This implies that the VC dimension of G is at most 2D, and also we have that if the VC dimension of a graph is smaller than D, then this implies that G emits a certain H with parts of size D and 2 to the D. D and 2 to the D. Okay, so emitting such a bipartite, small finite bipartite graph H is a condition which, up to the small change of the parameter, is equivalent to having small VC dimension for this family. Okay, and so now the result, the original result of Alon-Fischer-Newman and Lovász-Szegedy, it's actually quite far, can be derived quite quickly from the existence of epsilon nets. So I want to sketch the argument and then explain how it generalizes to hypergraphs, or what is our generalization to hypergraphs. So now sketch, I guess, of the main theorem for arity 2. Yeah, sketch for k equals 2. So assume we are given a graph G, v1, v2, e. So which emits a fixed h. Yeah, so we fix h. We fix actually, sorry. So we fix h and we fix epsilon greater than 0. By the previous remark, we know that emitting h can be, the condition of emitting h can be replaced by saying that there is a bound on the VC dimension. So let's say the VC dimension of G is bounded by D. Okay, so up to some linear multiple, like up to D, let's say we can, instead of emitting h, talk about graphs of finite VC dimension. Okay. Then by basic arguments in VC theory, we can also look not just at the family of fibers, but at the family of the symmetric differences of the fibers. So we can look at the family of all sets of the form EY, symmetric difference with EY prime. So this is a subset, let me be precise here. This is a subset of V1, where Y and Y prime are arbitrary elements in V2. Okay. So the VC dimension of the family of symmetric differences can be estimated by the VC dimension of the original family, whose symmetric differences we are considering. So something like 10D should be sufficient. Yeah, maybe it's not optimal, but certainly enough. Okay, but now we can apply the existence of epsilon nets to this family. So we can take x1 through xn in V1. Let this be an epsilon net for this family. Okay. So now, what does it mean? So it means for any pair of vertices, y and y prime in V2, we have that if the measure of the symmetric difference of the corresponding two fibers is greater than epsilon, then we have that at least one of these xi's belongs to this set. So belongs to the symmetric difference for some I. Okay. Now this can be rephrased slightly. So we can fix S a subset of the set of these points, x1 through xn, and we let Bs be the set consisting of all fibers or of all choices of y in V2, such that xi is in EY, if and only if xi is in S. Okay. So we have a finite collection of subsets of this epsilon net, and we look at all those fibers y, which pick out precisely the set S from this epsilon net. Okay. Now, what is the conclusion? So the conclusion is that for any two fibers, y and y prime, which belong to the same set Bs for some S, we have that the measure of the symmetric difference of these two fibers is small, because they pick out exactly the same points in the epsilon net, right? So the symmetric difference doesn't contain any points in the epsilon net, so it's smaller than, so the measure of it is smaller than epsilon. Okay, so in other words, up to symmetric difference of measure epsilon, there are only finitely many fibers of E. Yeah, so we can phrase it like this. so up to symmetric difference epsilon, there are only finitely many fibers of E. This is a fundamental fact about families of finite VC dimension. Okay. But now we're essentially done. So now, given this finiteness of fibers, it's not hard to write an approximation for E in terms of boxes. So namely, we pick some point in each of the sets BS, and we consider the relation E prime, which is given by the union of the fiber at BS times the corresponding set BS. Okay, so this is the definition of E prime. Note that this is a union of boxes. Yeah, so these are subsets on the first variable. These are subsets of the second variable. And from our observation, we have that the measure, it's not hard to calculate, that the measure of the symmetric difference is smaller than epsilon. Okay, so this gives a decomposition, an approximation for the graph E by boxes. The only remark to note is that the number of the sets BS, there are only polynomially many different sets BS by Sauer-Schellach. So let me write it. So by Sauer-Schellach, only poly of 1 over epsilon many different sets BS. Okay, so this is concerning the polynomial bound. Okay, so now this is a proof. So you see, it's not difficult. The proof is, of the original fact is actually not difficult at all once you have epsilon nets. Now, what happens with hypergraphs of higher arity? Well, what happens is that there's no VC theory for higher corresponding to it, unfortunately. So we had to develop some. So for this, let me define VCK dimension. This is something that is implicit in the work of Schellach in model theory. So assume where k is an integer parameter. Okay. So assume we have F, a family of subsets of the product of k sets. So we have some arbitrary sets V1 through Vk, and we look at F, a family of subsets of the product. Now we can talk about the VCK dimension of this family. So this is the maximal D, such that there exists a box contained in the sets. So there exists some sets Xi, subset of Vi, each of size D, such that the box is shattered. So such that for all Y, a subset of the product of these sets, X1 through Xk, there exists some set in the family, so S in F, such that Y is cut out from the product by intersecting with the set S. Okay, so let's consider the VC2, the k equals 2 case, for example. So we have V1, V2, two sets, okay? And now, in order to say that the VC dimension, VC2 dimension is, let's say, at least 2, we should be able to find a 2 by 2 box such that every subset of this box is picked out, etc., is cut out by intersecting with some set in the family. Okay, so this is the definition. Now, of course, the VC1 dimension corresponds to the usual VC dimension. We just have one set and consider the maximal size of a shattered subset of this. But for this higher k, we have to consider boxes that are shattered by the family. Okay. Let me give you one quick example. So let's say we have FGH some subsets of square of some set to v square, sorry, some set v. So then we can define E a subset of v cube, a ternary relation, by stipulating that a triple xyz belongs to E if and only if we have an odd number of pairs xy, xz, yz belonging to the corresponding relation f, g, h, respectively. And I should have said this f, h, g are arbitrary binary relations. Okay, so then we define ternary relation in terms of these three binary relations. Then an exercise, it's not hard to check that the VC2 dimension of this E is less than 100, let's say. It's probably much less than 100. Okay, so we have this notion of dimension. Now I want to state a parallel for the two facts that we had for so for the usual VC dimension or for VC1 dimension. So the first fact was Sauer-Schellach. So either an analog of the Sauer-Schellach lemma for this higher arity generalization. Okay, so there is some weak bound that I'm aware of. So namely, if F is a family of subsets of a product of K sets, okay, such that the VCK dimension of this family is bounded by D, then there exists some epsilon depending just on this D bigger than 0, such that for all xi subsets of Vi, all of size n, so we look at boxes with sides, with all of their sides of size n, and we ask how many sets are cut out by the family from such boxes. Okay, so what we get is that there are at most 2 to the m to the power k minus epsilon different sets that are cut out from the box by the sets in the family. Okay, so we look at the products of the xi's intersected with S, where S is an F. Okay, so of course the maximum number would be 2 to the m to the k, right? Because we're cutting n, sorry, this should be n, because we are looking at boxes, k by n by n by n, k times boxes. So the maximum number of subsets would be 2 to the n to the k. So we know that there is a little trade-off at least for higher arities. In fact, the precise bound is not this expression, but we have an explicit expression which does generalize Sauer-Schellach in the case k equals 1. Okay, now what can we say finally about the analog of the epsilon-net theorem for this higher arity? And this is the key technical result for the proof of our generalization for hypergraph, the main theorem. Yeah. So we have the following result, which I guess we view as a weak variant of this epsilon nets for symmetric differences that I have discussed earlier. So we have that for any natural numbers k and d and any positive real number epsilon, there exists some n which satisfies the following. Assume we are given some probability spaces, Vi mu I, finite probability spaces for I between 1 and k. Okay, and assume that F is a family of subsets of the product. Such that the VCK dimension of this family is bounded by D. Okay. Then there exists some sets, a finite list of sets in this family of length given by this bound n, so S1 through Sn in F. such that every other set in the family, so every S in F, can be approximated in terms of these finitely many sets, plus some smaller arity data. So what do I mean by this? So precisely for any S, we have that the measure, okay, which measure am I talking about? So we look at the product measure. So we have mu1 through times mu k, the product measure, and we look at the symmetric difference of S with D, it is smaller than epsilon, for some set D, which is given by a Boolean combination of the sets S1 through Sn, and moreover, at most n sets in the algebra bk k minus 1, but these sets do depend on the choice of S. Okay, so in fact, we only need to consider smaller arity fibers. So let's say fibers with the arity at most k minus 1 are fibers of E. Okay. So this is the generalization. In what sense? Sorry, a quick last remark. So in the case k equals 1, this algebra, well, there are no smaller arities, right? The smaller arity is only 0. So the algebra consists of the empty set and the whole set. Okay, and then we get this result specializes in the case k equals to 1 to saying that there are up to symmetric difference epsilon, symmetric difference of measure epsilon, there are only finitely many fibers. So this is the result that we discussed earlier for families of finite VC dimension. Okay, and so this is a generalization. So we get that there is, we only need finitely many fibers of maximal arity plus some bounded amount of smaller arity data. And now Boolean combinations of such things can express any set in your family. Okay, but this smaller arity data has to vary, of course. So if only the top arity fibers are fixed, and the smaller arity data varies depending on the set and the family that you consider. Okay, and once we have this result, it is possible to, well, it's more complicated, considerably more complicated than in the usual VC dimension case, but this is the key technical result. So then it's possible to write the graph in terms of these k-ary cylindrical sets as discussed in the main theorem earlier. Okay, so okay, so I think I'm out of time, so let me stop here. Thank you very much.
Yeah, thanks very much, Artem. Very, very, very nice results and very clear talk. I'll have a comment, maybe a question, but maybe first, do other people have questions? If someone has a question, just open the mic and speak, otherwise it'll be too complicated, please.
So maybe I could ask something. So your main theorem, you said there was some hope of an effective constant. So some dependence on epsilon. What sort of thing might come out? I mean, would that be likely to be some sort of tower function, or
we expect an exponential tower, I would say, yeah. But the hope is that somehow, in fact, in that bound, there are hidden two parameters actually. So we have the number of these maximal arity fibers and somehow smaller arity data. And what we believe is that the bound for this top arity, number of the top arity fibers that we need is presumably much better. So the smaller arity things, they're going to be as better in the general hypergraph regularity, let's say. So it's going to be an exponential tower. But for this top arity, it should be considerably better. So I think Henry thinks it should be even polynomial. I would think say on the safe side, it should be an exponential tower, but of bounded height, where the bound of the height depends on this parameter, this VCK dimension. So it should be some VCK dimension maybe times something, I don't know. So that's what we expect, yeah. but yeah, it needs the proof already is a bit complicated, even with allowing ourselves to work like with ultra products and compactness, etc. So there is a Ramsey theorem that is used a number of times in the proof, and etc. But the hope why the bound should be better than just general is basically because well, this is something maybe from the model theory point of view, this is where this intuition, I guess, comes, is that the theory of random variables is stable, and stable structures satisfy better bounds for Ramsey theorem, considerably dramatically better bounds for Ramsey theorem. So I guess because we have some structural conditions on the relations to which we need to apply Ramsey theorem in the proof, we expect that it can be cut down considerably instead of just growing unboundedly the height of the tower.
Okay.
Yeah. We hoped maybe we should try to figure it out at some point. Yeah, but we were happy to finish it as is using compactness and cutting some corners. But yeah, so in principle, there's a strategy how to finitize and extract more effective bound.
Okay, I had a question about another epsilon as well, which so you had this generalization of Sauer-Shallal. I wondered how good your numbers were in that. So again, is that? Oh,
you mean the actual what is the actual epsilon here? Or
I mean, is it something of that? I mean, is that the right behavior, or again, is it something? Yeah.
We think it is. Yeah. In fact, there are examples which show that you cannot do better than something of the form k minus epsilon. We don't know what this epsilon could be, and our proof probably gives epsilon which is much smaller than it should be. But already, like for k3 or something, you can, yeah, roughly this is the right behavior. But we don't know what epsilon should be exactly. But you only get a some trade-off of the power. It cannot be anything drastically better. So we have examples for that.
Okay, thank you. Very nice.
Any other comments or questions? Okay.
Maybe I could make a quick comment just please, because I actually promised to say a couple of words about the hypergraph regularity, but I didn't have time, unfortunately. So I just want to say one quick sentence about it. Is that so a way to reinterpret the main theorem, which also actually has a converse, as long as we allow ourselves to vary the measures. So the result, the main result can be viewed as characterizing the level, the arity of pseudorandomness in a hypergraph regularity decomposition. So if you think, like, roughly speaking, hypergraph regularity tells you that we can decompose the indicator function of the hypergraph in L2 norm, let's say. We can approximate it by a certain pseudorandom component of full arity. And then we have, let's say, certain a bunch of relations of all smaller arities, right? So we look at projections onto smaller and smaller arity algebras. And so what this result tells us is the level at which it characterizes, essentially, level at which pseudorandomness disappears. So it tells us that you only have pseudorandomness up to k, let's say, if the VCK dimension is bounded. You only have pseudorandom components up to k. So you have edges, triples, quadruples, etc., up to k, and above you don't need any more pseudorandom components. Above you only have structure component in the decomposition. And if in existence of such an approximation uniformly over all measures, in fact, characterizes small VCK dimension. So we have this characterization of the level at which or arity, if you want, at which pseudorandomness disappears in the hypergraph decomposition, after which it's killed, and this is captured precisely in this regime where you allow to vary the measures uniformly. This VCK dimension precisely characterizes this parameter, captures this parameter in the hypergraph regularity theorem. There's more about this in the paper if you're interested.
Okay, great. And now, yeah, if people would like to unmute and thank Artem. Thanks very much.
Thank you.